Hello everyone. Welcome back to another tutorial. Sorry this one's a little late. I had uh, a lot of stuff come up, really, over reading week, surprisingly. Um, but it's here now. And I actually condensed the information quite a bit. Um, there's a few things new in the framework that just make this easier. And I'll quickly go over them. Um, but for now, let's get into it. So I obviously have, I downloaded it and extracted it. So we're gonna pre-make build. Of course it did. And okay. All right. So what are we dealing with? Basically, there have been a few additions to graphics module. Actually, if we go to week 5 starter and main, you'll actually see new for this tutorial, directional light, point light, and uniform buffer. So, um, uniform buffers. They are essentially ways for you to just straight up send in a struct. And what I mean by that is, so if we look over here, I have this directional light object. Same type should be grouped together. So these are vec4s. And then you should always use vec4s. These were vec3s, but in your shader, vec3s get upscaled to vec4s anyways. So not storing it as a vec4 can mess up memory storage, or memory layout, basically. For example, actually, when I was setting these up, I actually had an issue where I didn't group these together, and these were vec3s. And so my value for ambient power was my final value for light color, and my final value for light color went into ambient power. So this was 1.0, and this was 0.02. And then my value for light ambient power, so 0.05 was actually the final value for ambient color. So this was 0.05 and this was 1.0. And that's just an example of what happens with memory being messed up. And you'll notice one new one that wasn't here in any other thing. This is shadow bias. We're going to be doing directional shadows, not point shadows. Directional shadows are by far the most simplistic of all of them. They're also the easiest to run. As you'll soon see, shadows can be intensive. Very, very intensive. My computer doesn't slow down at all, luckily. But you may not be able to follow 100%. I know that my old computer would not be able to handle the resolution that I'm rendering shadows at. Other than that, we'll look at Uniformbuffer.h. So actually, there is a neat little, comment that explains these. This is directly from, like, this is actually directly from my old tutorials that we were given. This is actually a comment block that I just took straight out of that. Because it is quite literally what explained uniform buffers entirely to me. And you actually have examples already. If we go into Otter Master Samples, Week 5 Resources Shaders, you'll notice Directional Blend Fong. So you'll see if we put these side by side, you'll notice struct directional light, light direction, light color, ambient color, ambient power, light ambient power, light specular power, and shadow bias. You'll notice that these are in the exact same order. The commons don't matter because commons don't take up memory. And these have to be in the exact same order. So what you can do after is you can just copy paste this into your work, into your shader if you want to use it. See, copy this struct and you can create a uniform buffer. See example that includes direction light. So this is a point light. I'm not using these because point lights, you have to decide if something's going to cast shadows or not. A point light requires that you render the scene a minimum of 4 times to get even in all 4 cardinal directions. Typically, you want up and down versions too. So typically, you render it 6 times, which is very intensive depending on your resolution, depending on your shadow map resolution. But yeah, so we're not doing point light shadow casting, but you can look into that actually. In your ILE, there's a page linked that will let you see how to set all this up. So yeah, this is point light. I don't use this at all, but I can. I could if I wanted to. So this is our directional light. You see we already have this in here. And then you see we have this thing, layout STD140, binding equals 0, uniform U lights. And so in this, I could actually put multiple lights. If I wanted to add point light to this, I could actually add point light to this. And make it so instead of just applying one light, it applies multiple in here. And that might be something that we show later, but for right now, no. Yeah. So you'll see directional light, and I called it the sun because a directional light is essentially just what the sun is. And then you'll notice I just call sun dot and then a value inside of the struct. It's the same as regular programming. Structs are basically identical. And when they're inside of this uniform block, you can just call directly. You don't got to do u lights dot sun. You can just do sun. As for how that's set up, well, it is wonderfully simple. So I create my directional light. That has all the default values. I create a uniform buffer. I called it directional light buffer. I allocate size of 1 directional light. And if I wanted to add more than just 1 directional light, like if we went in here, we wanted to add, typically you don't want more than 1 directional light, but if I did directional light sun 2, we now have 2 directional lights, so you just multiply by 2. And so this will allocate the size of 2 directional lights. And you basically just do that for anything, any amount. You'll see in here, actually. So the full size of this is 152 bytes. So you would allocate size of integer, size of Boolean, size of, I think it's, yeah, each float in each array. So arrays each value. If we look, where is it? In an array, every value, arrays are automatically aligned to 16 bytes per element, no matter how big that object is. So a float is only 4 bytes, but if you put floats in an array, it's going to be 16 bytes each. for a single float, 16 bytes, which is a little ridiculous. So what you would want to do instead of using an array, what you would do is you would quite literally just send in because like this is a three, like there's three elements in this array. You could just do a vec3 and it would cost 16, whereas this 3-element vector costs 48 bytes, which is not something you want. But yeah, you would add all these up, and that's what you would allocate here, basically. After that, I bind it to 0. You'll remember that I wrote binding equals 0. You can have, there is a max number, but you can have a bunch. It's the same as like binding texture slots. And that's pretty much it. So this lesson, I've condensed it a lot. It might even end up being under an hour. There is only 4 shaders to create and 1 file to edit. And that's it. I condensed everything a lot. I was going to make uniform buffers part of this, but there's no reason to like fully teach how to write them when we're doing something like shadows. I should be focusing on the shadows, obviously. I want you guys to focus on the shadows and not get caught up in the uniform buffer. You should be spending the week on shadows. And yeah, so we are going to get started. So the first thing that we're going to do, actually, we want to go back into shaders, and we want to so pass through has the least amount of code of any shader, and so we're just going to Control C, Control V. Oh, I didn't mean to open that. And then we're going to rename it to simple depth vert. I Control C, Control V, the wrong one. So we're going to Control C, Control V, pass through vert. I'm going to call it simple depth vert. And we're going to Control C, Control V, and name this one simple depth frac. Now these will both start with code in them, which is good. These are things that we want. And so what we're going to do is number 1. So all we want this to do is take the depth buffer. And we all know what the depth buffer is. We just wanted to use the depth buffer. So we only need position. We don't need UVs. We're not sampling anything. Then we need this thing called the light space matrix. So your backend in this sample has already been adjusted to send the light space matrix along with all the other stuff. Like if we go over here, go into utilities, backend.cpp, go to render VAO. So this is a light space matrix. I've made it so it defaults to just a default matrix in the case that it's not needed. This will make it so that none of your other render VAO calls break. I also added in so that shader.bind happens and shader.unbind happens. Because I don't know why it wasn't. It just should be. And then right here, you sent in light space matrix. Odds are this will be ignored for the mass majority of anything that you do. But that's there. That's there now. That's there as an option. It won't send anything until you teach it to send something. So what we're gonna do here is basically, so I'm sure you all know what the model view matrix is. Let's see if we can find it. Vertex shader. Here it is. So the model view projection matrix, the MVP matrix. And for your stuff, you mostly don't send in just projection, which is fine. But in some cases, you might need projection. So a lot of people send these in separately and then multiply them together in the shader because the shader is made to do math. What this is the light space matrix is essentially the view matrix from the point of view of your camera and a projection matrix from your camera. And now technically you can use the exact same projection matrix that you have with your regular camera. Did I say from the point of view of the camera? I meant from the point of view of your light. It's from your light. I'm sorry, that was probably confusing. But basically, here, I'll draw it. So just imagine that, so this is our camera. This is our camera. And this is all of our stuff. And then we have a light over here casting like directional light on everything. For the sake of light, let's just make it yellow. And let's say we place it right here with the direction going this way. So the way that we get our view matrix right here is we essentially, create a it's the inverse of your model matrix. That's what the view matrix is. Your camera's model matrix, the inverse of it is your view matrix. And so in order to make this work, to get the light view, what we do is we can do GLM has a function called look at, and we basically take the inverted position, so the negative, or not position, I screwed that up, the negative direction, of the light. So the negative direction of the light, so the current direction of the light goes from 0 to wherever the point is. It goes from 0 to wherever you're aiming. And then, so the negative direction of the light will get you a vector from 0 to wherever your light's quote unquote position is. So you get the negative direction, and then you pass it the center of your scene, so 0, 0, 0, or whatever the center of your scene is, and then you pass it the up vector for your world, so 0, 1, 0. Or wait, in our case, it should be 0, 0, 1. And from there, that returns a vector that is your light view matrix. From there, we just create a regular orthographic or a regular matrix or a regular projection matrix. You'll notice that for our camera, we use perspective because perspective works for 3D. But if we want shadows on things using a directional light, a directional light doesn't actually have a position. It doesn't physically have a position. You'll notice that I use straight lines, well, relatively straight, but you'll notice that I use straight lines instead of slanted lines like this for directional lighting. And that's because there is no fall off, there's no warping of perspective. So what the matrix that we're going to use for projection is we're going to use orthographic, which essentially means we will be treating our world as a 2D picture. And because of the way that we are going to multiply our light view with our light projection, because the way we're going to multiply those together, it will essentially allow us to turn any position. So when we multiply a position by these two together, multiply it, it'll essentially take the position in camera space and get where it is in light space. And that's why we call it the light space matrix. It takes, so this point is a vector from here to here. That's what this is. So what we're essentially doing when we multiply by the light space matrix is we are getting a vector from our light position to that exact same fragment. Let's draw it in blue. And this gets us, we will get that exact same fragment, but in this image. And basically from there, we basically draw the entire scene from the light's perspective, because if the light can't see the ground or the object behind it, that means that that object is occluded according to the light. That means that there should be shadows. And so what we do is, using this information, we can get the same point in the depth map as we can in our world using the camera. So what we do is we simply check, hey, right here, what's the depth value? Like what is this? What's this depth from the light, and what's this depth from the camera? And if the light's depth is less than the camera's depth, or wait, less than and greater than always confuses me. I believe it's the light's depth. So if the depth here, is if the depth here is less than what it is here, basically if there's something blocking this light, then we tell this fragment right here that, hey, you're being blocked out. There's no light hitting you. You should be dark. You should be whatever your shadow color is. And that's pretty much it. That is that. So from here, that's pretty much the gist of shadow mapping. So GL position is equal to light space matrix times U model. And don't forget, we always multiply in reverse order. So this would be light space matrix is equal to projection matrix times view matrix. And then it's model matrix times view matrix times projection matrix. And that gets us an MVP because we multiply in reverse order. And then we put it in position 1.0. And then in the fragment shader, didn't realize I had that open still. We don't actually need anything. So the best part about this pass is we are not going to render color at all. We are not going to render color. Thus, our fragment shader just needs to exist. Matrix, yeah. We just need this to exist. This just has to exist. That's the only rule. So now we have two new two new things. So what we're going to do is we are going to, and I'm going to load these in above this one. So shader, smart pointer, simple depth shader, shader create, depth shader, load shader part from file, depth vert, gl vertex shader, and then we're just gonna Control C, Control V, and then fragment shader, and then we're gonna select this. I'm gonna change it to simple depth frag. I just Control C, Control V that, by the way. Shader link. There we go. We now have a simple depth shader. And so what we're going to do now is we want to go down here. And remember how I mentioned that we're going to have a frame buffer for shadows? I'm going to call this shadow buffer. And so what we want to do is go all the way down to here, to our basic effect. Now these are effects, so we're not going to care much about those. And you'll notice that we have resolutions here. And so what I'm going to do is I'm actually going to make 1080 or 1024 and then int 1024. So game object, shadow buffer object, scene, create entity, shadow buffer. And then shadow buffer equals shadow buffer object dot place frame buffer, and then shadow buffer dot add. We're going to add a single depth target in it, and then shadow height. This allows us to have specific control over our shadow's resolution and not have it tied directly to the size of our screen. Because sometimes your computer can't handle rendering your scene twice. So you would you would have a smaller resolution for your shadow width. You wouldn't want this being resized with everything else. From there, we need to make sure that we clear it. Don't ever forget to clear it. So shadow buffer dot clear. And last but not least, we need to set up our light space matrix. Well, not last, sorry. This is only the first part. Light projection matrix. So we're just going to do GLM ortho. And for me, this is enough. This guarantees that this orthographic matrix will cover the entirety of our screen or the entirety of our scene. Why is that an error? 1, 2, 3. Oh, oops. Forgot the second. So negative 20, 20, negative 20, 20. Because GLM ortho takes in the left side of the screen, the right side of the screen, the bottom of the screen, the top of the screen, and then the Z near value and the Z far value. And in orthographic, your Z near value is actually negative because it goes basically half the screen if it's 0. So you want it to be big enough or small enough, I guess. From there, we need to create our next part. GLM. Remember how I talked about GLM look at? So we're going to do GLM vec3, and then we're going to take the sun and negate it like we talked about. Get the light out, light direction. And then our center of our scene. And then last but not least, our up value. And then it's GLM map 4, light space view projection. And I named it this just to make sure that like you can see it. So we multiply the light projection matrix by the light view matrix, and that gets us our light space matrix. We're actually basically done rendering this. Next up, all we need to do is GL viewport. So what this does is it sets the viewport so that OpenGL allows your frame buffer to render, allows everything to render to properly. It sets the size because our frame buffer that we're going to be rendering to is, if you remember, it can be smaller or bigger than our current screen width because I set it to 1024 by 1024. So what we're going to do is shadow buffer.bind. And then we are actually going to copy this, paste it, shadow buffer.unbind. And if I'm honest, we only copy pasted that for this. And what we're going to do is we're going to replace that with our simple depth shader. And then we are going to pass in our light space view projection matrix. And the other thing that we need to make sure to do, you see how we changed the GL viewport here? We want to make sure, if you notice up here, we actually get the window size. So if we actually do this again, we can make sure that it's always up to date because this one happens before our render loop. So you're like the size of the screen could have changed. You could have resized it in the time before that. So we're gonna do that, and then GL viewport 0, 0, and then width and height. And this will change your screen back to regular viewport. It'll cover your window now. Because this can actually, like if you try to render your shadow buffer, it might actually render outside of your window. Because this one, shadow height and shadow width, is actually bigger than my window by default, because our window is 800 by 800 by default. From there, that's, yeah. So if we build now, forgot to set a startup project. Now we just wait. This will take a bit. It's the first build. We are 30 minutes in. We're mostly done. We actually just need to implement the shadow calculations into our directional shader. But the reason why I ran this, gotta wait before I can bring over the thing. The reason why I ran this is to show that, obviously nothing's changed. The big thing, I reduced the amount so you could see the shadows better. I reduced the amount of like trees and stuff, just so you could see everything. But the reason why I ran that is so that I can go into Render Dock now. Go to Launch Application. Go to Downloads, Otter Master, Bin, Week 5 Starter, Launch, Allow Access. Still launching. Now we're going to print screen. I'm going to close that up. We're going to go to our depth only pass. And this is our output. This is the position of our light. You can actually see that it's the position of our light based on the way that the shadows are actually showing up. So shadows are on this side of the object and not on the top of the object, which means that the light isn't in front of the object, it is on top, looking slightly angled forward, just like this. Yeah, so that's all of what our function just did. And so if you see, you'll notice that it's 1024 by 1024. And then whereas over here, it is 800 by 800. So the depth is 1024. This one's 800 by 800. Yeah, figured that would be interesting to make sure that everybody sees. From here, it's pretty much just, so you know how we added the light space view projection. So we need to make sure that this sends into our main render now because we need it. And what we're going to do actually is so shadow buffer dot bind depth as texture, and I'm gonna bind this to slot 30, just so that I know I'm not overwriting anything important, no matter the shader. And then we just unbind texture down here. I put this in the wrong place. This needs to be right here. You cannot bind texture before you've bound your shader. Shader needs to be bound. So we're gonna bind depth as texture right here. Yeah. The biggest thing that we need to do now is we need to create a new vertex shader. Because our current vertex shader, actually we don't need to create a new one. We can just edit this one. So vertex shader, and then directional blend fong frag. So editing this vertex shader won't break any of your other stuff. I promise that. So what we can do is we are going to so the big thing that we want, layout location equals 4, out, back 4, out. Remember how I said that we could take in a position, multiply it by our, and this actually doesn't even need to, oh sorry, that does need to be there, for other things, possibly. It never broke removing it for me, but I don't want to remove it in case any of you are using it. So if we multiply a position by our light space matrix, we will take it from model view, from MVP space, into light space. So that's what this is. So what we're going to do right here, light space And so out frag position light space equals light space matrix times out pause. And so all we've done here is multiply the space that was already in the out pause, the one that was already in it was in model space. We just multiplied that into out pause instead of where we did right here. Instead of where we multiplied this by U model, we're just multiplying it by, see, U model's already multiplied into in position. So we're just multiplying it into out position. Alternatively, you could just easily just take this, multiply it into this, like replace it, like literally just write this right here, and then replace this. But we've already done the math here. There's no reason to not use it. Yeah. From there, we should also remove that. Don't need that. From there, what we are going to do is we need to set this up. So layout location equals 4 in vec4. So you see it's in location 4 in frag, and what did we name it? Let's just copy, paste. Frag position light space. And now that we've gotten that, we are actually going to create a function. You can actually do functions in shaders. I know, that's crazy. I'm sure you guys know this already, hopefully. But we're going to pass in frag pause light space. And down here, we're actually going to create an item called shadow. Make it equal to the return of shadow calculation. Pass in frag light space. And then from there, what we actually want to do is do shadow, or sorry, 1.0 minus shadow times diffuse and specular. So what this will do is, so wherever there's a shadow, wherever something's blocked out, it'll be black. It'll be a 1.0. And so what we want is to instead invert that number. So wherever there's a shadow, it just multiplies diffuse and specular by a 0. So what that'll do is it'll make it so that there's no diffuse light there where there's a shadow. That's all we're doing by inverting this. Alternatively, you could just swap out numbers that I'm sending in now, but the reason why they're returned like this is because 1.0 is true and 0 is false. So if there's a shadow, it's a 1.0. If there's not a shadow, it's a 0. If that makes any sense. Hopefully it does. So what we're going to do here, vec3. Oh, I almost forgot about an important thing. Layout binding equals 30 because we bound it to slot 30. Sampler 2D S shadow map. So we're going to write right here is we're going to do a perspective division, basically. It will essentially make it so our projection works with our shadow, because we're going from orthographic to perspective, and so we want to basically change that. So this is a vec3 equals frag pause light space dot xyz divided by light space dot w. Yeah, that basically just gets the So the way that we did this, basically, uh, it takes our so we took this and converted our position into light space using our matrix, and basically what we're doing here, with all of this, is we're just getting the out position of the same fragment. And so what we're doing with this is we're just making sure that this is a 1. We're just making sure that this becomes a 1. So if there's an issue with W and it's a bigger number, this will just basically make it so that it's a 1. And it'll treat it like that. And then so we're going to transform these values into a 0 to 1 range. So projection coordinates plus 0.5. This will get the closest depth value in that projected coordinate. And so basically, so float closest depth equals. So we're going to actually sample our shadow map. So we are sampling from the light's perspective using our projection coordinates x, y. Because if you remember, UVs are basically just they're percentages of position. So what we did here was we converted our position into 0 to 1 range so that we could use them as UVs instead of a -1 to 1, because that's how in perspective space, that's how positions are read in. It's -1 to 1. That's how vertices are read in. And so what we did here is we converted it to a percentage, and essentially are using this projection in order to sample our shadow map. And because it's depth, we only need one channel. And then so we get the current depth according to our camera. So float current depth equals projection coordinates dot c. So this will actually be the proper depth that the camera's seeing. This is the depth according to the camera. If it is less than what it should be, uh, like this should be a 1, if I'm honest. So if this is any darker than it's supposed to be, like in the camera, if this is any darker than it's supposed to be, then we know why. It would mean that check whether there's a shadow. So float shadow equals, so it's current depth is, if current depth is greater than closest depth, we either return, if current depth is greater than closest depth, so if the closest depth is less than current depth, then we return a 1. That means that there is a shadow there. If it isn't, then we return a 0. That means there is no shadow. And then we return shadow. And you'll notice that we've done all that now. So we can save, go over here, and run our program. Now that should have just copied all of your shaders. 1 second, I need to make sure it did. Because it's possible that we didn't flush main. Yes, it did. Well, would you look at that? We have shadows. Isn't that cool? But what's all of this? That's weird. That's really weird, isn't it? Well, okay. So there's an actual explanation for why it looks like this, and this is called shadow acne. We call this shadow acne. And if you'll give me one moment, I'm actually going to open up a diagram. there's a proper explanation for why we get shadow acne. Basically, so this is our light source, and our light source is going in. Sometimes this light goes underneath. Shouldn't, but um, uh, because of the depth, sometimes they can sample as because of like the sheer like distance from the light source. Sometimes they can sample as the same value. Um, uh, Basically, each texel. This is a texel, single texel. Um, Ends up being the same. Um, but the issue is that because it's rendered at an angle, normally because we don't end up having this issue, because here let's get snipping tool. If it's not at an angle, like if it's like directly above the object, we would end up with texels that look um, like this. Point is that the texels would not be having this issue. They wouldn't need to go into the object. They would just look like, so here it would be, and so on, and so forth. And so this we wouldn't have this right here. But because we have to do it at an angle, it goes into the ground. Now, there is actually a way that we can fix this. And that is called shadow biasing. And so all we do is we say, hey, there's a chance that this might be off by, a little bit. And you'll actually notice we already have shadow bias value in our directional light. So this might be off by a certain value. Hey, let's fix it. So let's actually fix that. So if we take current depth and subtract our sun dot shadow bias, and then we erase something random, put it back. Make sure to save in between. And this will make it so that your shaders get copied back over, because you've now changed the shader, and now you've changed main, so it's rebuilding part of the application. I'll wait for it. Now you don't have shadow bias. And you'll see we have perfectly nice shadows. And you have control over it with the light direction, and it actually changes actively with the light direction. You'll notice there's still some slight issues like this right here with Suzanne. This actually has to do with how the rocks are rendered, I believe. That's a rock right there. But it also has to do with the geometry on Suzanne, specifically. You'll find that higher complexity objects, I guess, if they have more concave places on them, you're likely to run into more issues. Convex objects, as you can see, really don't have any issues. And you actually notice that, as you can see, Suzanne's shadow will actually cast onto the rock. Other trees will cast shadows onto other trees. But you might be noticing one thing. They're very pixely shadows. Well, Um, this is a very normal thing. Because of the fact that this shadow was rendered at a fixed resolution, there are going to be hard edges because we're checking for every single texel. Basically, they're going to be hard edges. And now that actually brings me. We are actually almost exactly at an hour. That actually brings me to that's the end. That actually brings me to your ILE for this week. Your exercise. Oh, and another thing, if you want them to be less pixely, smaller pixels, another thing that you can do, I will show you this before we finish, because, we're under an hour right now. 4096. 4096. This is, oh, I did 50. This is about 4K. Well, kind of. I don't think it's exactly 4K. I don't remember what the exact number is, but it's a multiple of 4, or it's a base 2 number, so the computer really likes it. Computer really likes any base 2 numbers. But 4096. So now our shadow map is actually a higher resolution, and you'll notice those edges are way smaller now. Nothing looks as jagged as it did because we're using a higher resolution map than we are our screen. Our screen is a much higher resolution than our map. Or sorry, our map is a much higher resolution than our screen. And you can actually go further and you know, uh, 8192. That's just double 4096, I believe. 90. Yeah, that's double 4096. But now, every frame I'm going to be rendering and now they're extra small. The detail is even finer. You can barely tell. But the thing with shadows is they're not usually dark on the edges like this. Also, you have full control. Though making this anything more than, this is your Y value. Typically, I go with -5 because it is close enough that you get high quality shadows and far enough that everything is in the screen. But yeah, you can do this. Back and forth, back and forth. Oh, wait. I know what this is. I just realized what that is. That's actually that's not a glitch. That's actually the skybox. That is indeed the skybox. Because when we render our depth normals pass, our depth pass, the skybox shader doesn't get used. So it, but ideally, what you would actually want to do is add a, and I'll show this for, for the sake of importance. You can go into, if you go into, and you don't have to copy this. This is not follow along. You can just do bool cast shadows false. Render component set shadows bool cast shadows. Shadows, return this. There you go. So now I've just set that up, and you just tell it whether or not this object on the render component is going to cast shadows. And I'm gonna have it so, where is it? Render component, it defaults to true. We want it to default to true. And then we're gonna explicitly tell it, where's the skybox? Dot set cast shadow false. So now our skybox won't cast shadows. And so what we can do in here is actually just do if render dot cast shadows. Now if the object has cast shadows enabled, it'll cast shadows. If it doesn't, then it won't cast shadows. And that'll get rid of that little mishap that we have there. Now, go up into the air. See? Now the skybox doesn't get rendered on our depth normals pass, which means it won't cast shadows. We can actually showcase this another way. It's an object that actually exists. Where is Suzanne? Dot set cast shadow. So now the monkey will not cast shadows. You'll notice that now Suzanne does not have a shadow. And I can move this around all I want. Suzanne still will not have a shadow. And actually, you'll notice Suzanne will not have shadows cast on her either. Oh, wait, yes, she will. Sorry. That was misspoke. You'll notice you can still actually see her, and that's because of the ambient color or the ambient light. Remember how we, right here, we added ambient to our shadow. We can change this to red too. Red light. We can actually change our light to be slightly tinted based on the color of our sky as well. But that's not something we'll do here. But yeah. That's pretty cool. That is the gist of shadow mapping. I am surprised that I was able to get it condensed this much. That is pretty good. I'm pretty happy about that. And oh yeah, and it's not dependent. It's not like static. This is not baked shadows. This is brand new shadow map every frame. I can completely regenerate the light, the environment, and have different shadows now. Though, one thing worth mentioning is this world doesn't change at all. Well, it does if we regenerate environment, but normally it doesn't change. Um, so what you could do is you could just bake the map the first time, first run, and save the value. Um, but from here, actually, your ILE actually comes into play. And so for your ILE, I would like you to implement percent closeness filtering, PCF. And here is an image of what PCF is. They're just soft shadows. Soft shadows. They're just shadows that are softer, basically. You'll notice that all of our shadows right now are very hard, like this. Whereas we want them to be like this. So your job is to implement shadow filtering, or PCF shadows. Percent closeness filtering is what it's called. And it basically boils down to, and there's actually a pretty great tutorial by Learn OpenGL, and I actually link this in your thing. But yeah, all the work will be done in the shader. All your work for this will be done in the shader. You won't actually have to change a single bit of code. But yeah, that is all. I hope everyone has an amazing day, and I look forward to seeing you all on Friday. Bye bye.